This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning to everyone. It's the last week. Yeah, all good things come to an end, as well as bad things. So a few announcements before I start. Maybe a very important one is tomorrow we have the guest lecture from the IBM colleagues, as I announced via the LMS and emails. So as I said in my email, you are in principle responsible for the material at a high level. So please show up. Also, it's very impolite to not have an empty room for people who come voluntarily here to share their experience with you on industrial applications of optimization and machine learning. So I would like to have, as much as possible, a full room, unless you have an excuse. And yeah, as I said, being here also gives you a chance to meet them, get in touch, get the contact, and ask questions as well, right? So I will send another reminder today via email. So it's important that we have a good showing for tomorrow for the guest lecturers. The next thing is the workshops, marking, and the submission. I will create the submission link for the last workshop 4, which you are doing right now. That will be Sunday midnight, because I cannot put anything to SWOTWAC. I will ask the demonstrators to release the workshop 3 markings as soon as possible this week. And then the other one, because you're submitting on Sunday, they cannot do it instantaneously. They will need maybe 1 or 2 weeks. So it will be mid-June, well before the final exam. You will have all your scores in front of you. So that serves the purpose. If you have any issues with marking and so on, and mid-semester tests, you should come and see me during the consultation hours. Speaking of which, so we will have 3 consultations as preparation to the exam and answering your questions. I usually hold 3 of them. So we were just chatting with the audience here. So one of them will be in SWOTWAC, maybe 5th or 6th. I will announce it, of course. And then people said it makes sense. Our exam is on 27th, as far as I remember, right? 27th? Yep. So the week before makes sense. So I will hold it maybe Thursday 20th, right? The second one. And the third one will be 25th, 2 days before. 26th would be too much last minute, I think. Maybe 25th, 1 day before is even better. It's not good to leave everything to last minute like that. So these will be done 3 consultation hours where you can come and we can discuss your questions and have a good chat. I mentioned these. I think the fourth thing to talk about is SES surveys are open. I will also send a reminder. As I already sent an email regarding what I plan to do next year in terms of revisions, but there may be a lot of things that I missed. So your feedback is important. I act on it. You know, maybe you don't see the results, but you are paying forward. So you are helping the next generation, and the next generation helps the next generation. It's a bit like parenting. So don't think it is useless. It is useful. If you provide constructive feedback, especially written parts, then I really act on them. I take them very seriously. So it would be, I would appreciate the constructive feedback from you. And fill the SES surveys anyway. You know, you should create a difference also in terms of, you know, good instructors, bad instructors. If people put the effort, you should kind of give good feedback, encouraging it, and if people drop the ball, you should, you know, gently say it so people can improve themselves. Feedback is important, right? Good. Anything else? I think that's it from me for the arrangements. And we should conclude the discussion. I have also prepared this set of summary slides. I will go over giving a good summary, but also At the end of the summary slides, there is a study guide and exercise questions that I've selected. I will talk about those a little bit. And I will also post to LMS a study guide for the exam, repeating essentially what's in those slides. Any questions or concerns? Anything I missed? It's okay? All right. We were talking about Markov decision processes. Let's, that's a big topic, but let's go over it, refresh our memory till the point we left. So we have now, from the multi-armed bandwidth, which didn't have a concept of state, now we are in an environment, agent interacting with the environment. That is the key characteristic of reinforcement learning, right? Agent takes some actions and observes, gets some rewards from the environment, and the environment has a state. The observations of the agent are modeled with a state, and then a state of the environment changes based on the actions of the agent. So agent changes the environment, right? That wasn't the case with the bandits. Bandits are what they are. The agent doesn't have an influence on the environment. In many of the reinforcement learning settings, you have an influence on the environment when you play a game. If you have a robot, if you have a system in an environment, you change the environment a little bit. So there is this whole state action reward, state action sequence, right? That's how the thing evolves. It's a sequential process. You can parallelize and create multiple sequential processes, but essentially this is the fundamental idea. Now, if we model the environment with a finite Markov chain, then we have the and then it will be a probabilistic model where you go from one state to the other state and get a reward. The probability of getting a reward and going to the next state S prime, given the current state and given the action, that gives this transition probabilities tell us how the environment evolves based on our actions and also based on other factors. The environment also may have its own dynamics, right? Even if I take an action that is not terribly effective, the environment still may evolve, right? It's a combination of the two. And then we can write the state transition probabilities, expected reward, and then the state action, next state, all these expected rewards for given different things, or taking expectation, finding the marginals, and I gave this example. So the reward business is these rewards are instantaneous. We define the concept of returns over a finite horizon. Maybe I'm at time t. What return will I get until time capital T? That would be the GT, the adding up the returns. Or if I have an infinite horizon, if I add infinitely many things, these rewards are positive, you will blow up. The rewards, everything will be infinite. Therefore, a discount factor is put gamma less than 1. So you get a discounted reward. The idea is future rewards are discounted because they are far in the future. They don't have an immediate effect on me. Kind of have a more myopic vision. I focus on the immediate rewards a bit more than the future rewards, which get multiplied with gamma square, gamma cube, gamma less than 1 de-emphasizes them. So then given a policy, there are these important state value function and action value function, just like before we discussed. So we define these under a given policy, what would be the VS and QSA. That depends on the state and action. So what is my expected reward under that policy? Expected pi GT given the state and GT given, which is the return, given the ST and the action. How do we find then these policies? We use the Bellman's equation and principle of optimality, and I will come to this in a very concrete setting now. Before we write that, actually, we can write the value v pi s as going just from the definition and taking the marginals. We can actually connect this v pi s to the next state's v pi value function, current action value with the next state, right? Expected next state. So there is that relationship, and we will use this relationship. So these backup diagrams may help you. You know, it was in Sutton's book. It's not a bad idea because these formulas can be a bit cumbersome. If you see here, I am at state S under the policy pi. I take one of these possible actions, and based on the action chosen, the probability, transition probability, because it's S and A, it will give me a reward, and I will go to the next state S prime. So this is nice kind of visualization of what's going on here. And then you can have other type of diagrams here as well. And now we want to look at how we are going to the direction of how do we find these optimal policies. Before going there, solving this reinforcement learning task is actually informally finding a policy that achieves a lot of reward in the long run. But all the exploration, exploitation trade-offs, learning the environment, all of those apply, right? If you don't know the model of the environment. Even if you know the model of the environment, as we are doing now, right, there's a Markov chain. Even if I know it perfectly, finding the best policy is not that simple, right? I was giving the analogy of knowing the rules of the chess doesn't mean you know how to win in chess, right? So that's the, I think that's a good analogy. We actually can define the optimal state value function and optimal action value function, which is defining it easy. You just take the maximum over the policies, this gives you the optimal, and then maximum over policies, that gives you the optimal action value, Q star and V star. That still doesn't solve my problem, it's just defining it. And as you can expect, this relationship we established, Bellman equations, hold for both of these value functions, state and action value functions. And then now we are coming closer to the whole thing of finding these policies. In order to figure out whether a policy is good or bad, we need to be able to evaluate the policies, right? So that's where we are going to do first when we do the dynamic programming. We need to evaluate these policies. So we have the environment, agent, model, Markov chain, which we know. In this case, we know the Markov chain, right? This is classic MDP. And that means knowing the environment perfectly and very well and observing the states after taking actions. We have used this idea of, I introduced the idea of dynamic programming, principle of optimality. I chop the problem into smaller pieces. If my action now is optimal and I'm on an optimal path, that will mean that if I go one step further, I'm still on an optimal path. That gives me an iterative point of view. I defined the value functions and the action value functions, and then their relationship to this Bellman equation, right? So this is the Bellman equation that I'm talking about, and it also holds for the optimal versions of it, where we maximize over the policy. Now, dynamic programming actually provides this set of algorithms that I wanted to put this sentence on black on white, that can be used to compute optimal policies given a perfect MDP model of the environment. When you have a Markov chain of the environment, we take it as a perfect model. All right? Of course, modeling errors are there, but we kind of ignore it now. In order to find the good policy pi, the pi star, the best policy, I need to first be able to evaluate the policies and make the predictions. So compute the V pi, the value function, right? For any policy, I should be able to evaluate them in order to find the best one, right? How do I do that? There are actually a couple of ways of doing the policy evaluation. One is you can actually, given the policy, so you fix the pi, optimal or not, we don't know, then if you write this equation, definition equation, right, so which we have been repeatedly rewriting, this is the same equation that appears again and again with this model expected GT return given the state, because this is the value function that only depends on the state. The action value function is just, the difference is you have an A, it also conditioned on the action. And GT, you can write it this way, right? This is the definition. It depends on GT plus 1. And with the simple tricks that we discussed before, we can connect V pi S to the V pi S plus 1. And then take an expectation, there is the V pi S prime appearing here. So there is this connecting the two things. And if I write these equations for a given pi for all the states, I will have enough equations to solve for the V. So I can solve actually a set of linear equations. That can be a bit cumbersome. And that's but it's still a legitimate way of solving computing the v pi given a pi. Now, another way of doing it is using an iterative method and approximate the value functions starting from an initial value function and iteratively solve it. And the funny thing is the iteration is directly coming from the equation. So if I iterate with an index k, vk is k equals 0, k equals 1, 2, 3, and hopefully as asymptotically it gives me the right value function. Vk plus 1s will be then depending on the vks prime. So this vks on the right hand side will give me the next vk plus 1s. I use the same Bellman equation to iterate the value functions to approximate them iteratively. And that is a powerful idea. It's better than solving a set of linear equations. If you have too many states, then that linear program is huge in terms of number of variables and size. So people actually go with this path, and which brings us to our policy evaluation. So how do we compute the state value function for an arbitrary policy? It's called policy evaluation in the DP literature. It is also known as the prediction problem. That connects to the whole little bit of prediction thing we were doing in the bandit case. So the input pi algorithm, we want to come, we cannot, is an asymptotic algorithm. I come close when I converge. If I'm close enough, the value doesn't change much anymore, then I stop. Right? I come close epsilon, or delta in this case, delta close to the optimal value. And then that I say it's enough because I don't have infinite amount of time to iterate this. So start with a, delta equals 0 here. The whole trick is nothing but iterating with the formula that I have given, and then for loop over all the states, iterate and check whether the distance between the previous one and the current one are big enough. That means I'm making progress. I should continue. If the distance becomes smaller and smaller, converges when the maximum distance between the two iterations becomes small. Essentially, this algorithm is implementing that. Then I stop. So it's not an infinite loop. And then that is actually creating a good enough, v pi value function under a policy pi. Okay, that's good. So under a given policy, I know how to calculate my value function. But how do I find the best policy? I'm still not there yet. One of the keys to find the best policy is actually the policy improvement theorem. That gives us a very good clue as well. And this is a very common sense theorem. What it says is, for all the states, if the q, this is the action value function, right? Q pi s, and this is under the old policy pi. So there is an s, but I take actions according to a new policy pi prime of s, right? So this is the new policy pi prime, and pi is the old policy that I have. If I follow this pi prime of s to choose the actions, and if then this becomes a function of s. So this is actually same as having v pi prime s, and if this is giving me higher values than the original value function, that means the policy is better. That's very kind of common sense, right? If the policy is better, I'm getting better action values, and then that means you can actually show through this proof sketch that then v pi prime of s is greater than v pi of s. I've only included this as an extra information here. It's kind of straightforward, but you just do the substitutions. It's good to go over it, because if you want to see a little bit what's going on with these formulas, it's just a matter of substituting the formulas in their places. If this is true, I'm getting better results under the new policy, then the value function under the new policy is better than the old one. Yeah, it's almost a tautology, right? It's kind of common sense. Now, is this clear, the idea? Idea-wise? Yep. So you can go through the formulas later. And now we come to the interesting parts. I still don't have how to find a way of finding the best policy. The idea is we can find a new greedy policy pi prime that is better than old pi, right? How can we do this? We can actually do this by taking actions that look best in the short term after one step look ahead, according to the value function under the old policy. So the old policy has a value function. Pi has v pi, but I can use that to improve the policy in a greedy way. Remember, the greedy way is just taking the best action, maximizing the Q value, as in the case of the bandits, right? We were choosing the action that maximizes. That was the greedy policy, right? Here, what we do is we have a Q pi SA under the old policy, because that's the subscript Q pi. But if I have the action, this is now, the actions are still open. It just tells me if I choose this action, this is the value I'm getting at that state. If I choose that action, I'm the value getting at that another state, S2, S1, and so on. If I fix the state and then look at my action options at that state and choose the best one, maximum one, and choose the action that gives me the maximum value, argmax A, then that can define my next policy that is greedily better than the old policy. Right? Again, it makes sense. And when we put it down, notice that we can actually open this up and write it using the exact same things over and over again. These formulas are the same formulas. So there is one set of formulas that are repeatedly used here. So there is nothing new here. Then you have the argmax A, and you take the marginal of this value, right? So this new policy satisfies the policy improvement theorem, because this is exactly as we expect. This A, choosing it as a max, will give us a greater value. Therefore, if this is satisfied, then it is better, right? So essentially, if I greedily choose the action that maximizes Q pi at any given state S, that is a policy improvement, a policy variation. Greedy, that's a greedy variation in the old policy, pi prime from pi, and then that will give a better reward, as you can expect. And if this holds, then this holds as well. That's a policy improvement. So policy improvement theorem holds, right? So we know that it is as good or better than the original policy pi. I'm doing a max action, so that's kind of, again, very intuitively clear thing I'm talking about, right? And moreover, policy improvement must find a strictly better policy, because I'm taking the maximum, and then choosing the action that gives the maximum as well, argmax, except when the original policy is already optimal. If it's the original policy optimal, then the max will give me still the same result, so there will be no improvement. It will not give me worse results. You know, if my policy pi is already the optimal policy, then if I greedily take the argmax, the actions under that policy will be the same as actions under the optimal policy, because they will be already the max policy, right? So therefore, that is also something to note here, right? So the thing that will, I boldened this and put a 3-star here because this will become relevant. What I'm doing is I'm choosing a greedy policy while, you know, the value function that I'm using to choose the greedy policy was calculated under the old policy. Maybe I used, you know, under the old policy pi, I used maybe this policy evaluation to find the value function under that policy. I predicted the V's, V pi's, and now I'm doing an improvement using that V pi to find the pi prime. All right? So this is actually, we are coming to this whole idea of policy iteration under that. So I have a policy pi which tells me what actions to choose under what states, right? And then this may be not the optimal policy, it's just a policy. I can find the V pi iteratively, evaluate the V pi under that policy for all states, V pi S for all S. And then once I do that, that would be I can run this policy evaluation algorithm for that purpose, right? And then I can, you know, the policy improvement theorem says if I greedily improve upon that policy pi, whatever I am having, with a pi prime by taking the maximum, the action that gives me the maximum value at each state, then policy improvement theorem holds, and I should get a better policy. The pi prime is better than pi. That's good. I have now a way of finding the v's, and then using the v's finding a better policy. That's where we were going, right? We wanted to find the optimal policy. And one way of doing it is the very famous policy iteration algorithm. When you have in MDP, that's one of the two big algorithms. When you know the Markov chain perfectly, as I say, there are two things to be done. One is there are three things to be done. We can do the linear program that is cumbersome. Nobody almost uses that. But then iteratively, there are two things to be done. One is the policy iteration algorithm. What does the policy iteration algorithm do? It builds upon, and this is what you see everywhere. When you write MDP, you get the policy iteration. But I wanted to give you all these background steps for you to grasp what is going on with the policy iteration, because the whole idea is building upon what I've discussed. So it uses the idea of policy improvement, and it iteratively obtains monotonically. It never gets worse policies. It gets always better and better. Better policies through this process, and this process is policy evaluation and then policy improvement. This E arrow is evaluation, I arrow is the policy improvement. So start with the policy pi 0, random policy, right? You're taking random actions, given states. Then using again evaluation under the random actions, you get V pi 0. As we have discussed, that's the evaluation step. Then given the V pi 0, as we discussed, at any state, you can choose the maximum greedy action and to improve upon your pi 0 to get a pi 1. And that would be the policy improvement stage. So once you do the policy improvement, then you do an evaluation. Again, now you shouldn't use the V pi 0 again to improve things. Now you should find the V pi 1. And once you know the V pi 1, you again greedily choose the best actions at the states, which will give you V pi 2, and so on and so on. So you do this iteratively. And when you look at the algorithm, you initialize the value function and the policy and for all the states. Remember, this is a model-based, again, emphasize it again. This is model-based. You know the Markov chain of the environment, all right? So the second step is policy evaluation. I highlighted. So essentially, we do the same policy evaluation we were doing in the previous slide. That is what we use to take the pi 0, which initializes to something, and then finding our policy value function, right? And then we take this value function that we find, v of s here, and then we do a policy improvement. So what we do is, for each state, right? So is policy stable? First, this is just one way of implementing. There are some implementation details, but we go over all the states. We take the, we find the pi of s policy, current policy dictates the old actions, and then I do the action selection based on the maximized argmax, which will give the new policy based on what we have been talking about, this policy improvement. If the old action is not this new action, then the policy is not stable, right? Because I have made an improvement. They have coded it as unless it's stable type of thing. You can code it in different ways. You can say it isn't converged. Convergence is false. Then iterate until convergence. And when does the convergence occur? When all your improved actions match the current actions. You can actually make it this way. You can iterate in different ways. With the condition can be defined in different ways. Here they have done in a certain way. First they said they assumed it's stable, but then whenever they see it's not stable, then they said it's false. I should iterate more. And the iteration, this is the improvement. So this value function that is evaluated for all of s, v of s, then goes here. And this value function is used over the s prime, where you take the expectation, and then this p function is the model that you know to give you when you take the argmax of a, gives you the new policy, and this policy actually afterwards goes here back. So that is the iteration back and forth, that this whole thing is actually in the code. It's like that. Goes forward, goes back, goes forward, goes back. So because you're looping the whole thing, right, over and over again. So steps 2 and 3, you see else go to 2. So you go back to 2, evaluate again, improve again. If there is no more improvement to be done, you stop. But if there is improvement to be done, then you go to evaluation again. Okay? So this is classic policy iteration. Your Markov knowledge is actually here. The Markov chain knowledge is modeled here. You need to know this PS prime and what is the expected next, what is the probability of going to next state S prime and getting a reward R, given that I'm in state S and taking action A. I need to know this to be able to do this trick. So that's why it's classical. All right? So the sister algorithm to policy iteration algorithm is value iteration algorithm. Once people have done this, which is kind of a logical following up from the problem formulation, people also realized policy evaluation can be stopped after just one update of each state without losing the convergence guarantees. So this policy evaluation that I was doing up here, this whole loop over all the states, until repeatedly doing it until you reach the convergence, people realized, I don't need to do this whole loop until convergence. I can actually stop earlier, right? So once they realize that, then that saves a lot of time, and I can combine the policy improvement and truncated policy evaluation steps in one step. So you can merge them. So what's happening here is the VK plus 1 of S, so I'm updating my value iteration, right? But I embed this maximization of the action into the value iteration. So I use the same value iteration as before, but I embed this maximization of over A into it. So because it was like this, I was using the evaluated pi here, and then pi was coming from maximization in this loop. So I'm merging the two loops and then doing this value iteration, and then take the max here, and then this is for all the states. So I need to loop over all the states again at least once. So then the algorithm itself is then for estimating pi, to obtain the pi star. So I loop over for each state, then update this V of S, right? And then until I converge, and once I do this, which is combining the two steps, because I'm not just doing an evaluation, I'm also maximizing A here. I'm also doing the improvement in the same loop. So I'm in the same loop, I'm concurrently doing evaluation, iteration of the value function, approximating the value function, and I improve my policy because I take the maximization over the actions here. And once this converges nicely, then the deterministic policy is the one that gives the argmax of this for all the S. So once I have the value function, actually finding the policy is trivial because I can find from the policy value function, actually also action value function directly, I can find the best policies. The value function of the states gives you the cost landscape, return landscape of the whole state space. So remember, at any state you get an expected reward, but we are looking at over a horizon. We are not doing a myopic optimization here. So there is a state space. I take an action, and then the system moves to a new state, right? So even if I let's say I do infinite horizon discounted cost, so if I take an action, I shouldn't choose the myopically greedy action of giving me immediate best reward, right? I'm looking at my long-term returns here. So therefore, initially, I don't know the long-term return landscape of the states, of the state space. Only through this iterative algorithm, the value function V of S tells me this is the value of this expected value of the state, or action value function of this. That's even more useful because QSA for each state tells you if you take this action, then this is your long-term reward. If you take that action, this is your long-term reward. And looking at those, you can actually greedily choose the best action that gives me the best long-term reward. So what we are doing here is actually also calculating those long-term rewards, right? And then it is not immediately obvious. Let's do the chess analogy. I guess I like this analogy. So when you play the chess pieces, you may maybe have an opportunity to take the other parties, like you are white, maybe you can take the black's knight, right? But that is only an immediate gain for you. If you can predict what will happen down the road, will taking the black knight allow me to win the game or not? You don't know it initially. What we are doing right now is actually calculating that. So will the taking black knight will make me win the game, right, over the whole game. So that's kind of the counterpart of what we are doing here with the value, these value function approximations, and then improving the policies accordingly, right? So this is done with the policy iteration. Everyone has his own loop. Things are very clear, but it's not efficient. So when we merge things, they are a bit messier, but then they are much more efficient computationally because you don't run separate two loops losing time. Questions? So at this point, like for this stuff, I am obviously, because we are not solving problems here, I'm obviously going for a conceptual understanding what's going on, because there are very well established libraries for all this stuff, and you can use, download and use them and implement them for your problems. But I think as engineers, good engineers, it's important to get the fundamental ideas behind this whole stuff. And this is classic stuff again. Like when you go to Sutton's book, that's also a classic book. I think that was a nice discussion during the consultation hour. That people were saying, oh, but there is not much of a modern deep reinforcement learning in that book. That's true. They have only a small discussion at the end. It's a very hot new topic, so I'm giving you the cutting edge stuff next. But this is not the hot new topic. This is classic stuff. The hot new topic didn't emerge out of the blue. Actually, all the things they do build upon these classic ideas. They put a new twist, as we will discuss, and then got much better results. But at the end of the day, everyone doing reinforcement learning knows these basic algorithms. Like everyone who's worked their value know what is a policy iteration is, what is value iteration is, what do you mean by a model-based system taking these expectations and expected rewards and action value functions, policy improvement theorem. These are the fundamental building blocks that you should be familiar with when you want to do reinforcement learning with a, knowingly, right? Not just downloading a script and running it. So in that sense, I tried to clarify a lot of stuff here. When you read the book, it's kind of messier, and then you can go to the details of individual pieces, and you should maybe. But I think hopefully this will put you in a good position to demystify stuff that you read afterwards. That's my goal, to empower you with some fundamental knowledge so you can go and read stuff without getting confused about it, or you can put them to their places. Hopefully. Any questions to clarify things, or does it sound okay, this whole sequence of thinking at the first glance? Yeah, you should go and study a bit more, but that sounds good too. Now we come to the model-free reinforcement learning. That is important, and that is the thing that everybody is excited about these days. So we are in the hype cycle of model-free reinforcement learning. Actually, I have students started doing research on hybrid approaches where you have a partial model, and then maybe that will be the next big thing. But for now, as of 2018-19, model-free reinforcement learning is the king in town. 10, 20 years ago, model-based one was all the classic stuff is classic for a reason. Everybody was doing that. The Markov chains and hidden Markov models and so on. Now, it's very easy to not assume complete knowledge of the environment. Actually, creating the Markov model of the environment is a huge modeling task, as you can imagine. Especially if you deal with a real task, there are too many states anyway, then you need to find this huge transition matrix. Even if it's sparse, a lot of zeros between transitions between the states, that's still a huge task, and learning that environment. So it's much easier to not know the environment, just having a environment to interact with. You can still define the states, but then the transitions probabilities between the states, you kind of skip it and just observe it from the environment, right? So even model-free methods have some type of a model, in fact. It requires only experience, the sample sequences of states, actions, and rewards from actual or simulated environment. All right, so it can be actual environment or simulated environment. Most of the stuff these days is done with the simulated environment, and it makes a lot of sense. I will come to that why. So it is kind of very, very fancy stuff if you think about it. You have an environment, you don't know anything about it, and then you can still get the optimal behavior after trial and error and experience, right? So that's the very fundamental reinforcement learning. And we have now machines that learn playing chess by themselves, by playing with themselves. So that sounds like almost like magic, right? So that's pretty good stuff. And now we will know how to do it. A very important thing that I put here is it's easier to simulate the environment than have a complete description of the environment. So what I mean by that is, you know, having the complete probability distributions of state transitions means you need to really have to have a deep knowledge how the environment as a system behaves. It's much easier to define the states and then simulate the environment, which will also give you how the states are evolving, but you are only creating the rules of the environment, kind of like having the rules of the chess. So most of the games, most of the interesting games and systems have simple rules, but when you put them together and then when you play, the capability of, you know, having deep knowledge about the environment, that's a big, yet another big task, right? So the all possible transitions required for classical MDP, that can be impossible to obtain, but you can easily simulate the game or system. Okay, so that is that's what people have been doing in the model free. So I've put the slide from AlphaGo because there were articles saying Go will never be solved in our lifetime. So because of the complexity of states, there are too many states, right? Easy to describe the states, but then the number of states are explosive, and then the state transitions rules of Go are pretty simple. You can actually easily simulate a Go environment and interact with it, right? Interact with the Go environment. But then people say this is too big, too combinatorially explosive. We will never be able to solve it because the decision tree is huge, and it turns out it was solved. So then it's now solved at more than human level. So that's a huge achievement. So it just shows you model-free methods can actually do pretty good things. When we go to the model-free methods, then there are two things that are crucial, two concepts that are crucial to go back. And these are also classical concepts used again in modern settings and appear. One is the Monte Carlo methods. I was going to go a bit deeper into this, but I decided not to do that, just to give you the concept in a couple of slides, what this Monte Carlo thing is about, because there are a lot of Monte Carlo based variants of modern reinforcement learning. So the idea is we use averaging of sample returns. And how do we generate the random, what do we do in Monte Carlo methods is we generate random sample paths, episodic experiences, and learn from them. Essentially, you randomly choose some actions, right? A sequence of actions, you create an episode, and then you try to learn from them, right? So the idea is the same. So at the end of each episode, you evaluate the values. So we have the same evaluation and improvement episodes, but the Monte Carlo policy iteration alternates between them. So how do you generate these episodes? You use the Monte Carlo random selections, right? So then after each episode, you observed returns are used for policy evaluation, as we discussed. Then the policy improved at all the states visited in the episode according to this, which is essentially what we have been doing before. So there was this GT, that is the expected return at any time t for a given state that I am at t, and then I update my value function accordingly. So right, so they sample and the average return for each state action pair, just like the bandit methods, but now we have multiple states, so we need to do it on a state-by-state basis. So it is quite similar to the bandit methods in that sense. So you kind of create some experiences a bit randomly. So you use this randomness to embed this randomness into this evaluation improvement, policy improvement iteration, right, in the Monte Carlo. So if you consider a Monte Carlo version of the policy iteration, then classical policy iteration we discussed, what would be the Monte Carlo version? So we have some concepts like epsilon greedy policy, which is same as the bandits. So you choose the most of the time action that has maximum estimated action value, but with probability epsilon. Remember, in the classic policy iteration, we choose the maximum. Here we do it with epsilon greedy. Or greedy one is the one that is doing the maximum, but if you use in the Monte Carlo setting, then you need to embed the exploration. If you just do the greedy, we have the problem of not doing exploration. So people have came up with methods to do exploration on top of it. In epsilon greedy, it's already there, because with probability epsilon, I'm exploring. If I do the greedy policy, Sutton's book has all this stuff about exploring starts. You first explore and then do greedy and so on. So there is a lot of classical discussion there, which I'm kind of skipping, to be honest. But the idea of Monte Carlo methods for generating these Monte Carlo method of creating the sample paths and then Monte Carlo version of classical policy iteration. There are many papers also in the modern setting uses these fundamental ideas. Another concept that is important to know is on or off policy methods. An on policy method attempts to evaluate or improve the policy. Improve the policy, and then the policy that is trying to be improved is the one that is used to make the decision. So you have this decision making, the policy that generates the experience, and this is a general concept. A policy that is used to generate the experience is the policy that I'm trying to improve. So that is the on policy method, right? So I'm following a policy and then trying to improve that policy. That has advantages and disadvantages. And the counterpart is off policy methods. That means I follow a policy to generate the data, right? But then the policy that I'm improving is different from the one that generates the data. There is sometimes advantage to distinguish these two things. So I'm trying to improve a policy because I can generate the data and get the value function, and then based on the value function, I can improve the policy. I can do a policy improvement sequence, but I don't have to use the improved policies. I can still generate the data in a different way, right? This off policy method gives you that additional freedom, whereas in on policy, you kind of follow the policy that you have used, that you are improving to create the new data. At the end of the day, there is an environment to be interacted with. So Monte Carlo, I just want to say only this much about the Monte Carlo methods, and then more important thing to mention is the temporal difference learning, and that's at the heart of, according to Sutton as well, that's at the heart of reinforcement learning. The temporal difference learning is methods directly learned from raw experience iteratively without waiting the end for the episodes, right? Classic policy iteration was, episodically, I go through the states, I kind of go through all the states in an artificial way, see what's going on, I evaluate my policy, find the policy improvement. Temporal difference learning really embeds you to the environment. You become a bit more naturalistic, so you are part of the environment, experience it, and then without a full model of the environment dynamics, and use this raw experience to improve, figure out what is the best thing to do, right? At the theoretical level, the artificial one connects with the more natural one. And the TD prediction actually iteratively estimates the value function given a policy according to this. And if you notice, this is not terribly different from the Monte Carlo version of the improvement. So in that case, you do a GT, which is an expectation. Here, you just take an iterative, like a Bellman equation here. Actually, it is a Bellman equation because VST now depends on the immediate reward and the VST plus 1. So that is a Bellman iteration, right? It connects the value function at state S to the value function at the next step, T plus 1. So that is the whole value function idea. So and then if once it iterates V star, then they will give me the optimal path. So the whole thing then, there is the simplest version, TD0, is input the policy to be evaluated, and then that's the starting point, and then we have initialized the sum of the stuff, and there's a step size. Then we now iterate not over the states, but we iterate over the episodes. In that sense, it's a bit like the Monte Carlo. We have an episodic experiences based on my walking around the environment, and then we initialize the states. Then we iterate not over all the states, but all over my experience, recent experience episode. For each step, I take the action, observe the Rn S prime. If I take the action, what happens next? I improve my value function, and then that is the simple way of estimating V pi for a given pi, right? So this is the estimating stage again. So remember, we were doing in policy iteration, we were evaluation prediction stage, and then the policy improvement stage. Now in temporal difference learning, I am not doing it over all the states. I don't have the environment model, right? All I'm doing is taking actions, see which state I'm going next, and what reward I'm getting, immediate reward I'm getting. So that is the conceptual difference. So in the classic full model case, policy iteration, etc., you iterate over the states, you know the transition probabilities. Here, I'm already raw in the environment. I'm not iterating over the states. I'm just creating experiences in the temporal difference learning. I don't have a model of the environment. I only have my iterative way of estimating my value function. And first, in order to be able to get better policies, first I need to estimate, given a policy, what is my V pi. And I do that through my episodic experiences, taking the actions according to pi that I'm giving, and then doing this iteration, until my episode ends. Then if I have time, I go again and play it again, get more experience, and then estimate my V pi. And now that I know V pi, just like in the policy iteration idea, now estimation prediction part is done. What am I going to do with the policy improvement? There are a couple of options. One is the SARSA, state action reward action, is an on policy TD control algorithm. So now it is on policy. That means I'm using my SARSA policy to generate the next episode. Okay, that's what on policy means. And what do I do to create the new policy? Right? How do I do that? I actually do this. So I actually, instead of V, I go with Q, which is QSA. It depends also on the action, right? And we have the similar, actually the exact same formulation. Instead of V, you have the Q version of it. But what I'm doing is, I'm not given an initial policy, right? I'm not doing an evaluation. So I initialize, then choose A from S using policy derived from Q. So this is kind of, maybe I should have put a red thing here as well, because this is the key here. So once I have a Q estimate, from the Q estimate, I can choose a greedy policy or epsilon greedy policy to choose the best actions. based on my Q. Because Q tells me at a given state, if you choose this action, that's the value you are getting. If you choose that action, you're the value you're getting. Remember, at any given state, just like bandits, you have only finitely many actions to choose from. So you can take the max of those. That would be your greedy policy at state S, according to the current Q that you have. Right? So that tells you, for any given state, actually, that gives you a greedy policy. And you may say, oh, I don't want to do just greedy because that will kill my exploration. And if I don't explore, I will not learn my Q function. So we go back to the bandit type exploration-exploitation trade-off. Therefore, it's good to choose the actions maybe with an epsilon greedy policy. Therefore, I allow for some exploration because after I take the experience, after I choose the actions, right, then through each step of the episode, I need to, after I take these actions, that I then choose the action, take the action here. Taking the action gives me the new reward, and I go from state S to S prime, the next state. Maybe the next state is the same state as well, that's possible. And then choose the A prime from S prime, then I do it SARS essentially, state, action, reward. Then the next state is S prime, the next action is A prime. So I do all the steps. And then using these, I need all of these in order to now improve my Q iteration. So I need to do this iterative estimation of the Q values. And then these Q values give me then the next state is this, the previous action is this, and then I go through the episodes as much as time allows. So essentially, I'm time limited with this whole thing. If the environment is very complicated, then I go through the, I do this exploration and improve the estimation of Q at the same time. And the policy here will be then the epsilon greedy. Right? So, and you can choose a large epsilon in the beginning, then you can decrease it, so then you can trade off the exploration exploitation also dynamically in this scheme as well. So this is a very fundamental TD learning SARSA scheme. That's an on policy control algorithm. And just before we give the break, I think it is appropriate to talk about the Q learning, which is the very famous one. This is actually the SARSA was an on-policy TD control. Q-learning is an off-policy TD control. In SARSA, the actions that I'm choosing come from Q, and I use these actions to generate the experience, which I'm using to improve Q. So therefore, the actions that I'm creating, the policy that I'm improving is used to create my experience. Okay? So I'm using what I'm improving. As I said, there may be disadvantages to this. Q-learning is actually an off-policy TD algorithm. In this case, the learned action value function Q directly approximates the Q star, the optimal action value function. That's what we want, obviously. There is a Q star that we really want to find. But it is independent of the policy being followed. So actually, I can follow some other policy that doesn't come from Q, and I still compute the Q and find the best action. So below, A prime is not chosen from policy. All right, that the previous one, A prime, was chosen from choose A prime from S prime using policy. The next action that comes from the next state is obtained using the policy derived from Q here in SARSA policy. But in Q-learning, it is the same, almost the same algorithm, take action, observe, and so on. But then this is for action A. For action A prime, right? The A prime is not chosen from the policy. I actually choose this max QS prime A to find this value here. So that is the formula here is different from the formula here. Right? So I take a max here. So I greedily choose actually here the best action. So whereas for A prime essentially comes from a greedy optimization here. So A prime is not chosen from the original policy, which is could be, for example, again, a epsilon greedy. So that creates an off-policy deviation. And apparently, this is a good thing to do. In practice, this disassociates your exploration and episode generation from the policy improvement. If you have done control, I kind of find this a bit like, sometimes such separations are good. Where do we do it? We do it in control theory, for example. The observer dynamics are separate from the control dynamics. There is a bit of that going on here from system theory analogy at a deeper level. In system theory, you also try to learn an observer, and then you try to control the system with an observer system, and you want to keep the observer dynamics separate from the control dynamics. If you think about it, what we are doing here is also a bit similar. So I need to control my actions. In the off policy, these control dynamics of generating my actions are different from learning the policy actions. So policy improvement estimation actions. So there is a separation that's created. And that is actually a very fundamental point that also plays an important role in modern deep learning. So that's the story. I know I packed too many things, almost too many things here, but I want you to kind of like a skipping stone on top of the surface of a lake. I want you to not drown in it, just step on top of it, get the main ideas. The main ideas are actually quite simple. The difficulty is usually in details, proving the convergence of these things in many cases are difficult. The math needed for that is difficult. That's the mathematical part. And also some of the model-free stuff, you cannot actually prove anything because it's model-free. You cannot go with the math. Then the experimental verification of this stuff, you need to do many experiments with many different systems and problems to convince that, oh, my algorithm is better than your algorithm. That's what people do. Or you have a game to solve, in a well-defined setting, like a chess game or Go game, then you try to, win against a human being, then your performance criterion is obvious. If you win, then you're good, or if your algorithm gives you good results. So you can have these independent performance object, possibilities. So to recap, the model-free one, we don't know the Markov chain anymore. Classical methods don't apply, but they still apply in spirit. The Bellman equation, dynamic programming, iterative approach, they're all there. I still need to estimate my value functions, action value functions. I still need to improve my policies. These fundamentals are the cornerstones. In the model-free, I don't know the environment, but I still have the states. I observe what the environment is doing, even though I don't have a model of the environment. And I run iterative algorithms, alternating maybe sometimes between evaluation and improvement. Maybe I generate my, sample paths in a random way, episodic experiences in a random way, and then use those to learn my value functions and improve my policies. I can use epsilon greedy or greedy methods. But if I use greedy, I need to make sure I still explore. There's a lot of discussion on that, which is a bit kind of historical, to be honest, in Sutton and Bartow. I need to also know the concept of on policy and off policy, which is fundamentally, am I, walking around the environment according to the policy I'm improving, which is on policy, or am I walking around the environment according to some other method? I deviate from my optimal policy that I'm deriving through this estimation and improvement process, which brings us to the temporal difference learning. The prediction method is quite similar, but unlike the classical methods iterating over all the states, this is better also when you have too many states to iterate over. So you just create experiences and iterate over them and use iterative algorithm to estimate your value function. So under a policy, and then how do I improve the policy? Again, we come back to the same thing. We improve the policy in the SARSA with an on policy method. I update the Q function like this. I follow on policy. People say, oh, why not do this? This seems logical, right? But then people realize, okay, this doesn't work always well. And then they say, why don't I do an off policy version and then don't choose the next action from my Q function, but I greedily choose the maximum here to update my QSA, and that is giving Q-learning. People observed that gives really good results because of the separation. I kind of gave a bit of intuition on that separation. I find it, from system theory, and the Q-learning is the one that people, because that was the kind of a pinnacle of the classic methods. Then when people did the deep learning version of the reinforcement learning, they started with the Q-learning actually, because that they started from the state of the art. Notice that there is a table here before I go. Let's give a break of 10 minutes. We can continue in 11:20. Right? And we are almost done, so the day has ended. But don't go away.
What is when you say policy, what does it look like? Is it just an if-else statement?
Actually, it is very simple when you have the Q action value function, QSA. Then at any state S, you have a Q value for any given action. And then, for example, if you want to be greedy, you can choose the max of those, and that gives you what to do at any state.
So that's policy.
That is a policy, isn't it? At any given state, you know what your next move is.
Okay. So in the bandit case, your policy is if else. So
your probability of choosing which arm to choose, right? Or at any, there is no state there. So you probability of choosing each one.
So policy is
Or
not like-
choosing, it could be deterministic, right? I always choose this one.
Oh, so that's a policy.
Yeah, epsilon grid is a policy. I can actually have a policy that is balancing the two terms. That's a good question. I will start with this next. But you get it, bro?
Yeah, so it's just like it's just a. It's just
But
like
if it's an
concept.
else, but if you know the value function, you know everything there is to know, then you immediately choose your best next option.
Yeah. Okay.
Finding that value function is the difficult thing.
Thank you.
Yep. All right, let's continue from where we left. Okay, the last but not least, deep reinforcement learning, right? You know, if you put a DNN into anything, then it becomes deep. So you can have, you know, if you put a deep neural network into anything, then it becomes a deep something. And then in this case, deep reinforcement learning, as you can imagine, has a DNN into a deep neural network in it. So where does it come into the play? Notice the classic Q learning, right? So classic Q learning is for environments that have complicated tons of states, right? You don't have a model of the environment. But what we have here, notice that when you run this algorithm, it's not clearly obvious from this pseudocode, but there's a QSA. That's actually a table. You know, for each state, and you know, action, that's the value. Like for each state in the maybe in the row, and then actions in the columns, then entries would be the Q values, right? And then once I have that full table, I may not have a model of the environment like a Markov chain, but having the full table of QSA for all the states in the environment, a converged QSA, will automatically give me the best actions, right? My policy then will be just looking at the QSA at a given state. What is the action that gives me the best value? That's the one I'm going to choose because that's my option, you know, original idea in reinforcement learning. Just like in the bandit problem, where I choose the best action once I know everything. Of course, the issue is in reinforcement learning, learning never stops because the environment is very complicated. You never have a complete picture. And then, therefore, you're always iterating and bettering your Q estimates. So there is always this trade-off between exploration and exploitation. You shouldn't be always greedy, prematurely greedy, because then you kind of shoot yourself in the foot. You don't get a good Q value estimates, and then your table will be a bad table, and from the bad table will come the bad policy. But if you are spending, on the flip side, if you spend too much time on exploration, maybe you get a good table, but you lost your time exploring and you didn't get good rewards. So that's the trade-off, right? In practical problems, when computers play Go or chess, again, coming back to the simple examples, you're bound by the computational power and time you have. You know, if you work for Google, let's say, if Google gives you a rack of computers, that's your computational power, and if your boss there gives you 2 weeks, then that's your time. So you need to find the best policy and best value function in that 2 weeks. That will give you the result, right? So those are the constraints of the thing. These loops, episodic loops, are dictated by those external factors, how many episodes you can process. If you're a big company, as I was giving the example of Google, then you have a lot of resources and maybe a lot of time to burn. Now we come to the deep reinforcement learning, right? So this is actually, stuff is 5 to 10 year old. It's pretty new. And then builds upon, of course, upon the classic ideas. But the thing is, people realize, because of the thing also I mentioned, classical methods require a model. Creating a Markov model becomes infeasible as the state scale, obviously. So people got excited about temporal difference learning, model-free approach. And then in the temporal difference learning, Q-learning is the most popular algorithm. But even in Q-learning, the state action spaces need to be small enough that the approximate value functions, the entries of the Q action value functions, right, the QSA functions, they should be small enough to be represented as arrays or tables. So we need to store them, right? The DQN, actually, as I say, combines RL, reinforcement learning, with deep neural networks and builds upon the classical ideas. So, and it also brings some new aspects. It's just more than just embedding a deep neural network. It also has some couple of nice tricks. And then it is DQN itself building upon classic Q learning. It's a model-free TD. It's a temporal difference learning approach. It's model-free, and it's an off-policy method. because it builds upon the Q-learning, which is actually both of these things. But then it uses a deep neural network as a nonlinear function approximator to represent the Q values in the table. So instead of using a table to represent the Q values, I use a deep neural network to get the Q values. So if I give S and A to the neural network, it gives me the value, right? So, and then I need to train that neural network, of course. There's now this whole issue of training the neural network instead of putting values to the table. And it's an approximation, of course. The deep neural network, however expressive, is a sum, it's an approximator, function approximator. So people actually thought of this a while ago. The people tried, they already, this is not a big leap, right? I mean, if you do Q-learning and you have a huge table, and the artificial neural networks have been around for a long while, people said, why don't I use an ANN to summarize this table? People thought of this, but it didn't work out. When you were training, the neural network, it became unstable. The whole RL became unstable before. So these guys actually have, and the links are below, actually, I will show, they come up with this brilliant couple of nice ideas to overcome that. Actually, it's a technical issue. So this is good engineering work, as I was saying, right? Most of this stuff is good engineering, building upon classical good, knowledge. So the DQN, in order to make it work with a neural network approximating the Q function, DQN uses this couple of fundamental tricks. One is this experience replay that randomizes over the experience data, and then again using removing the correlations in the observation sequence. So this kind of takes this idea of off policy in one step further. So I collect some experiences, but then I put them to a memory, and then I shuffle them. Because the states can be shuffled, right? I mean, it's a state-based system. States summarize all the history. Still a powerful state-based model, even though I don't know how they are evolving. I don't have a Markov model, but I know that if I'm in a given state and take an action, then I go to another state with some probability, right? So there is this whole state-based approach, and I can put these experiences to store them and episode, and then shuffle them and learn from them. So that is the experience replay, and then iterative update is adjust these action values Q towards the target values only periodically. Again, then reducing some correlations. So all of these three things that are added up on top of the Q-learning brings us to the basic DQN algorithm. This is straight from the paper, which is linked in the bottom corner, and the paper is fully available, right? And this is exactly the algorithm I gave you in the workshop. So my workshop algorithm, I checked against this whole thing. So let's look at what's going on. We have this initializing replay memory, and then initialize a action value function with random weights. So you see already the wording here tells you that the action value function is a function that I approximate with a neural network. So that is my function Q is a neural network now, right? So then through episodes, then I initialize the sequence, and then in each episode, with probability epsilon, I choose a random action. So this is actually epsilon greedy, right? There is also epsilon greedy built in here. Because with epsilon, I choose a random action. Otherwise, I choose an action that maximizes this Q star, right? So there is that aspect as in Q learning. Then what they do is execute action in an emulator and observe the reward and image. This line is essentially, it doesn't have to be an image. You are interacting with the environment. So, and then you get your reward, and then move to the next state. That environment moves to the next state. Then I store my transition in my memory. Right? This is one piece of an experience as part of this episode. Right? Now, what I do is, after I do that, I sample a random mini batch of transitions from my memory. This is the memory replay business. So I get a random subset of my past experiences. This removes all the correlation between the experience instances, and then I actually give I get the update on the Q value from the Q value equation, the same equation as before, right? So because the original Q value was this, so I do this here the same way, and then I need to train my neural network as well, because the neural network needs to be trained to get the Q values, and then the experience and the is used to train this neural network. The experience that I obtained is trained to train the neural network with a square error, as you can see here, and then the gradient for training the neural network embeds the Q equation. Actually, there's you see the Q update is here used from this objective. The Q update brings the Q update is embedded to the gradient, which I use to train my to the neural network. Okay, I should rephrase this. So I need to estimate the Q value, right? To estimate the Q value, I use my past experiences. This is the same as before, but now my Q values don't come from a table. My Q values come from the neural network. So I need to train the neural network with the experiences so that my neural network approximates the Q value well. So then the QSA values. So this is done through a gradient, usual gradient training algorithm, and in the gradient we make use of this basics of the Q learning embedded. They appear through the square error. So that's the idea, and that's what we have done also you have done practically in the workshop, right? So you were given this whole practical story. DQN is not the only thing. This builds upon the Q learning. Actually, you can start from the policy iteration and policy gradients, and you can go to actor-critic learning. There's the advantage actor-critic, A2C, or asynchronous advantage actor-critic, A3C. I simply don't have, I ran out of time in the subject. So you can go and read, and I'm sure you will be in better position than before when you read that A3C, because it is building on the policy iteration ideas, policy gradient algorithms. So you do a gradient improvement on the policies in A3C essentially. DQN builds upon the classic Q learning. Two different pathways, as we were discussing: policy iteration, value iteration. Value iteration goes to Q learning in the temporal difference version, and if you go from the policy iteration pathway, you end up with the modern version would be then A2C or A3C. There are a lot of links. I think I put somewhere in the workshop or here. So this whole idea then, building upon what we discussed, it's just this twist and adding one more step to the whole picture. It takes also this in addition to putting the neural network, it puts the idea of really breaking all the connections between the experiences. So remember, we create these experiences. In that sense, it's a bit like Monte Carlo. The experiences are randomly created or randomized a little bit. In the off policy, the experience is not created according to the improved policy. Here we are actually we are off policy as well, but we also shuffle the experiences, which creates some of this randomness, breaking of the correlations between the learning process and the experience gathering process. So the learning process is not the data that is used in the learning process is now decorrelated from the experience process, because the experience process is sequential. So these sequences are breaking down when you do a mini batch like this, mini batch learning like this. So it is also can be a bit noisy, because as you can imagine, now neural network is an approximator. We are already approximating a Q function. We are trying to learn a Q function, and then we train a neural network to approximate the Q function. Multiple approximations going on. Neural network training has its own local minima, A lot of noise are created here. So things don't always work well immediately, right? And then you need to spend some initial time to train the neural network. So most of the RLL, reinforced DQN that you do, initially you need to do a lot of exploration to collect enough experiences. And once you reach some threshold of collecting enough experiences that is sufficient to train your network, and your network is good enough, there is a hint for the workshop, you need to have a good network to approximate the Q function, right? If you have a smallish network that is not expressive enough, then it brings a big bias and then you don't succeed. But if you have an expressive enough network that is enough parameters to play with, then and you accumulate enough experiences, after a point, this random learning ends and then your approximator becomes good enough and you start to get good results out of this. And then you can dial down epsilon exploration and get the fruits of your labor, so to say. Exploration, exploitation trade-off the same way. This is the original paper, actually, as I was saying, I always taught myself the computer games, because it's a controlled environment and you can run things very fast, is a really good playground for reinforcement learning, but also for AI. In general, not just for reinforcement learning, but AI in general. Computer games provide a really nice complex environment where you can test things and train things without any physical cost. You only burn electricity, right? So this DQN opened a new era, and then this is the first modern model-free RL method. A lot of variants came afterwards. As I said, there's the policy iteration versions, A2C, A3C. Then there's the double DQN, and people added up a lot of other ideas just to try. Does it work? Does it lead to better results? Because there are no proofs anymore. Mathematically, it's too complex to do anything with it now, with this level of complexity. So people just keep trying different things. And this trial and error, I suspect, will hit a wall after a point. And then we will wait for new developments in theoretical domain to kick off another round of engineering activity like this. What they did with the games is also very interesting. They didn't sit down and write an API. They actually played the game just like a human. So they took the pictures of the screen, and then with certain frequency, essentially they processed the video of the screen. And then, just like a human being, they put the convolutional neural networks initially to extract the features, and they also learned the whole interpretation of the screen, what it means. And then from that interpretation, you learn the whole, the whole Q values. So if there is a score somewhere in the corner, actually that is giving you, the success or failure. So it is really very powerful, right? If it's game over, you get it from the screen and so on. So the rewards and so on are also not coded explicitly. They are all implicit to the environment. So you really interact with the environment, and the environment is observed through the screen. The game screen gives you the same environment that a human player uses. So that's very powerful as well. So essentially stacking up all that image processing on top, then you don't explicitly program the environment interaction. You just use what you see. So then the results were comparable to the human game testers. So these things played many of these old Atari games. This is an Atari console, classic, right? So the old games. So it played them very well. People have moved on now to playing, complicated multiplayer games. Now you have multiple reinforcement learners as agents, and they communicate with each other, and then play the multiplayer games like Dota and so on, the real-time strategy games, and that's really complex stuff. It can be also worrying in your parentheses. If you play that complex stuff, you can also fight wars. So there is that. We are kind of going to dangerous territory as human beings. But we don't want to have the problem of a Skynet and Terminator, real life. But that's not. It's not there, and I don't think it will be there because these things are coming from what you just have learned. I should have demystified it for you. There is nothing more theoretical about what they are doing. Just good engineering on top of the theory that I just covered. Therefore, I don't think it will go that far. But if you do the next big jump in the AI, then we might be seriously in trouble. It's not there yet. This whole discussion about artificial general intelligence, which we don't even know what it means, but it's not too far away either. So it's kind of in the horizon, behind the scene kind of type of thing. We are not too far, and then we can get worried after. If someone does a big jump in theoretically connecting some of the things, yeah, you can actually get worried. For now, this whole worry is a bit premature. You can still do a lot of nasty things with this technology, but it's still simplistic. Just a parenthesis. So when you play computer games, though, it's very nice. And then I'm personally on a very positive note, I'm very excited about how we can take these technologies and instead of playing games, can we apply to engineering problems, especially complex engineering problems. That's one thing. And this is all model-free, so that's a disadvantage in my opinion. It's good to handle complexity, that's an advantage, but I still believe in engineering as engineering. So I'm also very excited about hybrid methods, like where we use the engineering knowledge, how we can use the engineering knowledge, physical description of the systems, and combine them with some of the model-free aspects to get powerful algorithms to go obtain scalable designs in engineering or solutions in engineering that are also a little bit explainable. Otherwise, we don't know what's going on. You just train a neural network. Neural network becomes your Q function. And once you have the neural network's output, the optimal strategy is obvious. You choose the actions that give you the best Q values, because Q values summarize for a given state what is the best, as you move with an expected return, right? Expected return over infinite horizon or finite horizon until the end of the game. So that's the whole thing. And it's still very mysterious. You just train a neural network. The weights are weights. We print them, but we don't know what they mean. You printed the weights. Right? It's part of the exercise in the workshop. You know the function, what the neural network is doing, but what does it? It's a bit like looking into your own brain. Looking at someone's brain doesn't tell you what that person is thinking. We don't have that technology yet. So a lot of big open problems there. But it's an exciting research area. Yep. So all right. So I ended up with sacrificed depth for the breadth in this last part. I covered hopefully some of the fundamental ideas, but ended up giving you the cutting edge stuff. I could have turned it, when I said a couple of lectures ago, it's easy to turn this to a history lecture and give you stop it at the Q learning, spend more time on these fundamentals, and then tell you, go and read the latest stuff. But it's not that simple sometimes. The latest stuff is not trivial improvements. These are good engineering achievements. Although it is done in the domain of software engineering, they are very, very good engineering achievements, which we should respect, actually, as engineers as well. Kudos to our computer science colleagues there. All right, so this is the technical part ending. In the last 10 minutes, I want to show these slides, because if I don't show slides, I guess people forget that they exist, even though I emailed them. So what have we done in this subject? And more importantly, maybe a study guide that is relevant to everybody. Will ask me, what are we going to do in the final exam, which is a fact of life, so I'm mindful of that. These were the objectives, and I looked at back. I think we haven't done bad with the objectives. We have made a lot of good progress in these objectives with our workshops and lectures. So I hope you are also happy with what we have achieved compared to what you didn't know in the beginning and now. I think there is a good difference. We have covered a lot of important, interesting stuff and done a lot of hands-on experience with the workshops. So it had three components: engineering concepts and applications, mathematical foundations, and programming. Programming part was covered by the workshops. Mathematical foundations and the engineering aspects were also in the lectures. I believe I emphasized engineering. Really, I haven't gone into depth in mathematics, believe me or not. Some people think I did, but There's deep mathematics in optimization, much more mathematics in machine learning. I can go very deep into Bayesian and probability theory there. And in the last part, Markovian processes, Markov decision processes. One can also go very deep mathematically there. For those who are mathematically inclined, those are kind of your future directions as well, right? Anything I haven't covered. This is the initial kick, so you can mathematically go deeper in each of the 3 sections of the subject. You can also obviously go deeper from a programming practical point of view. The workshops should have given you that perspective. There is much more to learn there as well. And the engineering applications and concepts, I tried to give as many engineering examples as possible in the workshops. That should give you an idea how I can apply it to some of my problems. I'm enjoying actually working with some student groups in capstones where they immediately apply some of this knowledge from the subject. So this is very applicable, useful stuff. There is a reason why machine learning is so famous. It's very applicable, it's very useful. It's not esoteric knowledge. I covered this is kind of, I copy-pasted these learning objectives. You should know about, from introduction, optimization, machine learning, basics, just to go maybe slowly. In the introduction, you should know the basic definitions of what means what. Then we come to optimization part, unconstrained basics and unconstrained optimization, fundamentals. These are the list of, I think, basic things we covered. Then we covered the constraint convex optimization, KKTs, duality, and so on, penalty methods and active set methods. We touched it a little bit. Then in machine learning, again, the basics. Then we did regression, model selection, Bayesian decision theory, what is maximum likelihood, what is map. As you have seen, some of these fundamentals repeatedly appeared. I'm hoping also when you look back, you should see the connections between the things. A lot of the optimization, we reused it repeatedly. A lot of the basic machine learning, we also used it in the neural networks and deep learning, not only in machine learning. And then in the unsupervised learning, we did the classical clustering and Gaussian mixtures and PCA, expectation maximization, which is very similar, right? Expectation maximization in spirit is very much what is doing what we were discussing just minutes ago in reinforcement learning. Expectation evaluation, then improvement, expectation improvement. This is in spirit the same idea in expectation maximization as well. So it's this iterative improvement process. Bias variance trade-offs, we did SVM, which is fine, important. Common metrics, this is almost like a hand guide. I put the metrics here. Logistic regression. Then the neural networks, architectures, the cost functions, optimization, backpropagation. Then we did the sequential data, which is also very important, maybe even more important for engineers, because I skipped all the image stuff, because that is already well covered popularly and in computer science. I believe the sequential data is more relevant to engineering, as the examples illustrate. So this regular stuff. I mentioned the Markov models because that's kind of a classical way of handling sequential data. And before this whole new era, hidden Markov models were the standard tool for speech recognition and translation business. That's the best people had. Then this whole RNN and LSTM stuff we discussed. I also mentioned CNN. Upon request, people say, why are you skipping it? So I included in a brief way how they relate to filtering processes, which is nicely connected to signal processing, actually. Then we did the reinforcement learning, as we have discussed, and I had to stop at DQN. So suggestions for study I'm giving here some, my personal opinions, right? So you can study as you like, but I think it is important to develop the conceptual understanding of topics. What bothers me most in our program is, in course, is we teach some problem-solving skills to students, but then you don't connect it to anything. And you don't know where to use that skill and what is the upside of that skill and what is the downside of that problem-solving skill. I think it's very important that you reach that maturity at master level. This is the tool, here's how I'm going to use it, what is behind it mathematically or program-wise, or theory-wise, and then where is it useful, what is its upside, what are its limits. You need to know that stuff. Conceptual understanding is very important. I think this is where things failed also for when it comes to even a math subject like linear algebra. Somebody gave you some linear algebra skills wherever it's coming from. It's a diverse audience. Some learned it here in Australia, some learned it overseas. But because you didn't connect it to anything, you all forgot about it. You didn't know what to do with it, apparently. And then you said, okay, the knowledge doesn't get used, it got forgotten. Math gets forgotten very quickly. So it shouldn't be the same for whatever you're learning, and hopefully not for this one. You know, reflecting on the equations, foundations, mathematical foundations, relating to concepts, the connections between the topics, you know, how optimization is used in machine learning, how optimization is used in deep learning, and how machine learning methods like the maximum likelihood is used again in deep learning, and how do you use, or in RL, and how do you use probability theory in all these places? How do they connect to each other? What is, you know, maybe that reinforcement learning approach, improvement evaluation, is not that different from expectation maximized. There are deep connections, at least, you know, at the high level. Read the books. If you just read the slides, you haven't learned anything from the subject. I'm going to be very frank with this. You need to go to the books and read relevant sections. I know you have limited time, and I'm also mindful of that, but I'm not saying go read all the books. I'm not even saying go read all the chapters. You need to go pinpoint-wise, find the resource, read the relevant part, get the knowledge. This is the skill you need to have in 21st century engineers. It's not about reading a complete, nobody will give you a complete book and then end of book questions and then solve these questions to learn the subject. The knowledge is out there. I linked so many of them. You should have the skill to learn about the subject, ideally by yourself. In this case, is a guided. I try to be your guide here, right? I give you the guideline. Here's the idea. Here's the topic. I hopefully give you the kernel of knowledge. I even give you the pointers, what book sections you need to read. You need to be able to do this in a guided way. If you cannot do it in a guided way, how are you going to do it when you are working in an unguided way? When your boss tells you, oh, you know, 5 years later there will be a popular new thing coming up, I don't know what. Then your boss will tell you, you're an engineer from a top university, right? And you have 5 years of experience now, work experience. Go learn this stuff. Then you're on your own. You will be your own guide, which is much more difficult. Here at least you have the guidance of the slides and the pointers and the links. You should be able to go and in limited time, yeah, it's a time constraint, get the most out of it. That's a skill you should practice. It's a very good skill. It's a very crucial skill. If you get that skill, it's better than the knowledge, because you can always get the knowledge then. Once you have the fundamentals. Solve problems. Okay, this is the part where we go, you know, as I call high school, and there is a final exam. You need to practice, and that's coming to the next slide. If you find the time, solve. Try to look at end of chapter questions. Practical skills, reflect your experiences in the workshop, because I like to ask, as you have noticed, about them. It really makes it very fun to see who has done the workshop and not done the workshop. And you were supposed to do the workshop or be there, right? And then preparing nice handwritten notes, helping, you know, writing handwritten notes helps retaining the knowledge. When we relinquished the whiteboard or blackboard and switched to this system, we lost something, okay? And then that's why I asked you to prepare handwritten notes for the final exam. Two sheets of A4 paper, that's 4 pages. That's a lot of pages. You can write almost the whole subject there. But it needs to be handwritten, not photocopied. Actually, there was a huge problem. Please don't bring, you know, machine-generated notes. The invigilators are very vigilant, you know, jokingly. It creates a lot of headache. So the notes should be handwritten, and because of this reason, when you write them down, you retain a lot of knowledge for future. So that's the idea. And then when I say these are the questions, 34 of them that I selected that are similar, possibly similar to the final exam questions, right? Some of the questions were, as I was saying during our course, they are more conceptual to illustrate a point. When I removed them, There are a couple of them with stars which have cumbersome parts. They then don't ignore the cumbersome parts. I will not ask you to take very complicated derivatives in the final exam. One of the questions is just a simple exercise in taking derivatives. But then I will ask you to know the basics of the backpropagation derivatives. They are not cumbersome, but they are structured derivatives. So then that's easy to do. The other one is just cumbersome, nothing conceptually. So these are the questions, which questions in which lecture, modules and lectures. So you can find them in the slides. You already have all the solutions to them, typed solutions and my notes. Okay? So that's the practical thing. Further study, it's mathematically further study. Optimization, if you want to study optimization, I don't know how, like you take a MOOC or you do PhD or whatever, you do another master. Deeper into optimization theory, Boyd, Bersekas, Dunberger, these are really great books if you want to go deeper mathematically. You can go to the path of global non-convex optimization, which is very interesting, stochastic optimization as well. There's a whole world of mixed integer and discrete optimization, which I haven't covered. There is a very nice subject actually on this in this university as well, that I know. In machine learning, you can use Bishop to improve your classical machine learning. A lot of probability there as well. Also probabilistic approach book like Barber, if you want to go deeper into probabilistic world of machine learning. But these are both classical stuff. Sequential models, I haven't done Kalman filters. I haven't done justice to Markov models. I only given you some pointers. What are the main problems and what are the main solutions? You can go learn them. Deep learning has a lot of computing architectures, stochastic and global optimization is interesting. Reinforcement learning, hybrid models I mentioned. Control theory is model-based, so you can learn control theory if you want to do the model-based approach. From a practical point of view, data science is something I haven't covered, didn't have time. You can learn pandas and go deeper into statistical methods and how you do data science. You are now empowered to do that, but you need to improve also your programming skills. Data science is very programming oriented. Deep learning, you can do TensorFlow directly instead of playing with Keras. GANs is something I haven't covered, very interesting topic, generative adversarial networks. All these deep fakes come from that. Whether those things will have an engineering application or not is still an open question. People just play with pictures these days with these. AI is a topic I personally find very fascinating. Russell and Norwick's book is classical for learning AI beyond machine learning, beyond deep learning, logical part of AI, symbolic approaches. They are not popular these days, but these things come in cycles, right? As I said repeatedly. So we may very well have a cycle where logic becomes the king and all this stuff people say, this was nice, but they had limits and so on. It might happen. RL has a lot of stuff. OpenAI Gym has so many problems. DQN extensions, A3C, AlphaZero is interesting. New computing, this is very futuristic stuff, new computing architectures. I believe the next big thing may come from these, but that's my personal opinion and I might be totally wrong. And engineering applications. So I think this will also, I'm pretty confident that these computationally powerful methods will seep into engineering. Because it makes sense. Like it's not, and to the extent whatever they are doing, right? So they are not all powerful. We all know the limits of these methods, but they do good things, and it would be impossible for engineering people ignoring these powerful computational methods. So it will seep into our field in some way. It's already power systems and so on. People use them extensively. Other areas may use them as well. So that's it from me. Thank you very much for your patience, and it's a great cohort. It was a pleasure teaching you. And don't forget the guest lecture tomorrow, right? Yes. Please show up.